All right, so I'm going to tell you how to find the extrema. I'm talking about maxima and minima, okay? The points of maximum and points of minimum. But first, I want to talk about local ones, and then we'll talk about global or the absolute ones. Okay, and the reason is because there are a couple of different things involved, whether you're looking for local or extrema, local or absolute extrema. All right, so first, let's look for local extrema. That would be the first priority. When you look at these functions, this is some sort of a cubic function, right? You can find the local extrema, local maximum here, okay, and you can see the horizontal tangent. You can see the local minima here. That's not a local minimum. This is not an absolute minimum because again the graph goes lower than that. But this is again where you can see where the tangent is a horizontal line, right? Now, when you have sharp corners, such as these two, then you don't have the same kind of a tangent line. In fact, there is no tangent line. Okay, so at this point, there is no tangent. There is no tangent here. So we can't always rely on the horizontal tangent, right? The derivative may not even exist at these points. Now, again, this is a local maximum and also an absolute maximum of this function, the parabola. And you can see that there is a tangent line and its slope seems to be 0. It's a horizontal thing, okay? And in fact, any local extremum would occur as one of these points. So these points are important, right? You can say C is a critical point. This is a very important term in calculus. A critical point of F, if and only if, remember for mathematical definitions, you want to use if and only if, so that you can characterize what we are trying to define. So C, the value of a point in the domain, C is a critical point of F if and only if F prime of C is equal to 0 or undefined. So whenever the function is not differentiable at a point, that point is a critical point. Or if it is differentiable and the derivative is 0, then that is a critical point. So at a critical point, the function has this property that its derivative is either 0 or it does not exist. And here's the theorem which makes the critical point so critical. Every relative extremum, so that's local. I guess I should be using the word local, right? Local and relative in this context mean exactly the same. So every local extremum, which means local max and local min, every local extremum occurs at a critical point of F. Okay, so this is cool, right? This is great because really to find any kind of maximum or minimum, the only places you would have to look are the places where the derivative is 0 or undefined. Okay, now there's a big warning, big warning I have to give you, right? It's the fact that you can't reverse this. The converse is not true, okay? So I should say not, again, not every critical point is a local max or min. Okay, just because you have a critical point, meaning the derivative is not existent or 0. Okay, just because you found a critical point does not mean that you have a local maximum or minimum. So make sure you keep this in mind. All right. So if A then B may be true, but that does not mean that if B then A is true. Okay. Here it's saying if C is if F has a local extremum at C, then C is a critical point. That's true. But you could not say if F has a critical point at C, then F has a local maximum or minimum at that point. Okay, that does not happen. All right, let's try to find some local maximum or minimum. All right, the first one, the easy one, sine of x. All right, let's draw a graph of this. Okay, what's the derivative? Is it differentiable everywhere? Yes, okay, because the derivative is cosine of x. And that is equal to 0 if x is pi over 2 plus, plus or minus, but plus 2k pi. And wait, that's true too, but it's k pi, isn't it? Because on the unit circle, this is k pi over 2, and then this is 3 pi over 2, and in both places the cosine is equal to 0. And that means you're talking about this point and this point and this point and this point, and of course you have infinitely many points. And look, at all of these points you have a horizontal tangent because the derivative is equal to 0, right? Derivative always exists and is 0 at these points. The critical, so these are the critical points. These are all the, oops, I'm not writing this, all the critical points of sine of x, okay? And roughly half of them, I mean, half of the infinitely many, these are maximum points. These are local maximum. They're also absolute maximum because those are the highest points where y is equal to 1. This is a minimum point, and so is this. Okay, I'm having a little issue with my computer, so hold on a second. All right, so you can see these are minimum points here, and there's another local minimum. Again, every one of these local minimum points are absolute minimum points as well, because the value of the function never goes below -1, never goes above +1, right? All right, how about f x is equal to x? Now, this is, of course, a straight line. The derivative is 1. It's never 0 anywhere. Okay, so here, there is no critical points, right? And if there was any kind of local maximum or minimum, it would have to happen at a critical point. If there is no critical point, then there is no relative, or I should say local extreme. No relative, no local maximum or no local minimum, period. Of course, you knew that because it's a straight line function, right? But you can confidently say that there is absolutely no local maximum or minimum of this. If you have a function, let's say this is number 1, this is number 2, this is number 3, the absolute value function, it's going to look like this. What's the derivative? Does the derivative exist? Well, yes, it does, right? It's not a simple function. Well, it is sort of simple. It is equal to 1 if x is greater than 0. It's -1 if x is less than 0, because the slope over here is -1, slope over here is +1, and it's undefined at 0. So the only critical point, there's one critical point, that's x is equal to 0 right here, okay? And is this a local maximum or minimum, or neither, okay? It turns out to be a local minimum and also an absolute minimum, even though we're not talking about absolute extremum yet, right? But there is a local minimum because you do have that critical point, and that happens to be where the local minimum is. All right, here's an important example to consider. When you have x cubed, you have this function like this. Okay, is there a critical point for this? 3x squared. This is defined everywhere. The function is differentiable everywhere. I mean, you know, this is a polynomial, so of course it's differentiable everywhere. But there is a point, in fact, one point where the derivative is equal to 0. And that's at this point. We are saying that if I were to draw a tangent, draw the tangent line at 0, 0, it actually goes through like that. So the derivative is 0 at 0. But you can tell that this is not but 0, but I should say f does not have a local extrema, local maximum or minimum at 0. So that's what I was saying. The converse is not true. If f has a local maximum or minimum, it would have to happen at a critical point. But just because f has a critical point does not mean that that's where a local maximum or minimum occurs. Okay, so yes, is there a critical point for x cubed? Yes, 0 is the only critical point, but f has neither a local maximum or local minimum at that point. Okay. Number 5, f of x is, now let's talk about the inverse function here. That's the x cubed function. It goes like this. Okay. And the derivative is 1/3 x to the negative 2/3, which is 1/3 x to the 2/3. Okay. Now this is never 0 for any x. But there is a critical point because f prime of x does not exist if x is equal to 0. What's happening here? It is a smooth curve, right? But the problem is right here, you can tell this inverse of this function. The tangent becomes the vertical line, which has slope infinite. And so there is a critical point, all right? X equals 0 is a critical point, and in fact, it's the only critical point. But f has no extreme, no local extreme. At 0, okay? So again, just because you have found a critical point does not mean that it's where a local maximum or minimum will occur. All right, let's do another example. I'm going to do 2 other examples. So here is a cubic function, 1/3 x cubed minus 5/2x squared plus 4x, right? Do you know what the graph of this looks like? No, I don't, okay? But I can share this with you. Okay, roughly speaking, you can use your graphing calculator to see the graph of this function. It's going to look like this. The derivative is easy to find. It's 1/3 times 3 times x squared minus 5 halves times 2, which is 5, x to the first plus 4, right? Now, this is differentiable everywhere, so this exists for all x. So there is no point where the derivative is undefined, but there is a place, maybe a couple of places where the derivative is equal to 0. And it's easy to factor this. It's 4 and 1. Okay, so you can factor this into x minus 1 and x minus 4. And so this is 0 if one of them is equal to 0. So 1 and 4 are the critical points. And these are the only critical points, okay? Which, by the way, means that there could be only 2 points, up to 2 points, where a relative extremum could happen. And it could happen at 1, it could happen at 4, it could happen at both, or it could happen at neither. So here's one point where the derivative is 0, for meaning that the tangent line is horizontal, and here's another point. Okay, and you can't tell whether these are relative maximum or minimum or neither yet. Okay, later we will find another tool, a couple of tools actually, to separate or to distinguish relative maximum, local maximum from local minimum. Okay, those are called the second derivative test or the first derivative test. But right now we don't have these. So you would have to depend on a graph or an XY chart or something. But you could say here from the graph, f has a local maximum at 1 and local minimum at 4. Now, these are not absolute max or min, because again, the graph goes higher than this point, whatever this point is. and then it goes lower than that point, whatever that y value is. Okay, so these are local max and local min and not absolute ones. But you could have, and you have found all of these. Okay, now how do you know that you have found all of the local extreme? That's because all those local extrema have to happen at critical points, and you have only 2 critical points, right, on the entire real line. So if somebody says, hey, you know what, I found that this actually kind of goes around this way. If you go really, really far, like when x is like negative 3,427, I found that it starts to go back up again. And you say, no, that is not true. And I can confidently say that, because if you found this, then this will be a point of local minimum, which means it has to be a critical point, which means this has to be 0. But we know there are only 2 points where it's equal to 0. Okay, and you can dispute with confidence such a claim or such a conspiracy theory thought. Okay, so that's one example. Let me give you another example to find local maxima and local minima. And after this example, we'll go into the absolute ones. This one is 4x over 1 plus x squared. Now, is this an what do you know about this function? Okay. First of all, you have x squared, so the denominator, it doesn't matter if it's positive or negative. The top is an odd function, right? So this whole thing is going to be an odd function. And that's nice to know, because if you know what one side looks like, you would know what the other side looks like. Okay, let's take the derivative of this. It is a quotient, so you should use the quotient rule, of course. The denominator is the easier one to do, so I try to get that over with by squaring the original denominator. The numerator is the derivative of the top times the bottom minus the top times the derivative of the denominator, right? So this will be 4 plus 4x squared minus 8x squared all over the original denominator square. I think we can make this a little easier. 4 minus 4x squared over 1 plus x squared square. And in fact, you can even factor out the 4. And in fact, you can factor the top more, 1 minus x and 1 plus x, right? Now, what do you know about the denominator? This is never equal to 0. Now, how do I know this? Because x squared is never negative. It could be 0, but it's almost always positive. It's positive or 0. If you add 1 to it, this is positive. Positive square is positive. Okay, so it's never going to be 0, which means the derivative is always defined. Okay, so f prime is 0 only when what? One of these is equal to 0. Well, 4 is never 0. So x is 1 or negative 1. So these are the only critical points of the function. Okay, 1 and negative 1. All right, and that's about all we can do at this point. Okay, we could say that 1 and negative 1 could be local maximum and a minimum, but we don't really know. But there are no other possible points where a local maximum or minimum could occur. Okay, so that information with a graph that looks like this, and this is actually the graph of this function, it's going to look like this. Remember, it's an odd function, so there is a symmetry with respect to the origin. And so this is what the function looks like. And sure enough, when x is equal to 1, and the negative 1, you see horizontal tangent lines as indicated by, f prime of x, right? Because f prime of x is 0 when x is 1 and negative 1. And it's always defined, which means the function is differentiable at every single point. Okay, and so from this you can say f has a local maximum at 1 and local minimum at negative 1. Okay, but once again, without additional tools, we really couldn't tell if these are local maximum or local minimum, or neither, right? But only with a graph at this point, you can find that these are indeed local extrema. All right. So now, next we will find, or we'll show you I'll show you the way or ways to find absolute maximum and absolute minimum points. For that, we go to the third segment of the video lecture for section 4.3.